Yes.
Okay. So, hi, thanks for the introduction. I'm really happy to be here. As you can see from my lighting, it's evening here, but that's all good. So, I'm Karen Jex. I'm a senior solutions architect at Crunchy Data, which doesn't tell anybody very much about what I do, my current job title, but my background as a database administrator. And mainly at the moment, I work with, play with, and learn things about Postgres and help my customers to do the same. So today, I mean, it's 2024, so it's almost obligatory. We're going to be talking about AI in Postgres, and in particular, trying to find out what is the opposite of a corn dog. I did this talk at a European conference recently, and I had to include this technical slide because obviously most of the people in the audience didn't know what a corn dog was, had never heard of a corn dog. So I explained to them that a corn dog is pretty much a hot dog on a stick, and I absolutely apologize for the technical errors that I'm sure are in this slide, and I hope everyone can forgive me for that. So hopefully the rest of the information in this talk is more accurate than that one. I already explained a little bit about who I am. So I've always worked with databases. Doesn't necessarily make me very interesting to talk to at parties, but hopefully encourages you to believe that I'm vaguely qualified to be here talking to you about databases. What should you expect from the presentation today? Magic is what I've promised people, or at least the magic that we'll get from combining the OpenAI API or another API of your choice, the pgVector Postgres extension, and combining that to incorporate AI into your Postgres database and over-engineer a solution, or our favorite thing to do, over-engineering solutions to a contrived problem. So the problem that I've come up with is how to choose new food recipes that will please a pizza-loving picky eater so the whole family doesn't have to eat pizza all week. And of course, as promised, unfortunately not the answer to the question of life, the universe and everything, but at least the opposite of what's a corn, with the opposite of a corn dog. So let's dive right in. What is pgVector? It's an open source Postgres extension. It's been around since 2021, I think, were the first commits, and it's in really active development, and we'll see as we go through some of the ways it's changing. It lets you store vectors in your database alongside your existing data, and it provides methods and operators that let you do vector similarity searches in Postgres. So it supports exact and approximate searches depending on what you need in terms of precision and performance. And if that doesn't mean anything to you at this point, don't worry, because we're going to go through all of that. And one of the most exciting things for me is that it's Postgres. It's just Postgres. So you get all of your normal Postgres features. You get your ACID compliance, your point-in-time recovery, indexing, and all of the other Postgres features that you're used to. So we're also using OpenAI. Most people have already heard of OpenAI, the AI platform company. It provides APIs for many different functions, and today we're using the AI for embedding or classification. Although OpenAI is what we use in the demos in this talk, you can use any tool you want that has an API for embedding. My colleague Reka did a really good lightning talk recently at PG Day Chicago, where she talked about using Hugging Face and the sentence transformer model as an alternative. This is a really crude illustration of how it all fits together. You send your data to OpenAI or your choice of AI model for classification, you get the embedding data back and store it in your database, and then you use the pgVector Postgres extension to query for what we call relatedness. So first of all, you need pgVector. Depending on whether or not pgVector is pre-installed in your Postgres distribution, you might need to install it before you do anything else. This is how I installed it on my Mac. I just followed the instructions in the README of the pgVector GitHub repo, and the README is actually really great. I've found it very useful. It's got a lot of information. This is the only bit of sales pitch I'll do today for Crunchy Data, who I work for. If you're using CPK, Crunchy Postgres for Kubernetes, or Crunchy Bridge, pgVector is pre-installed, so you can skip this step, and I'm sure there are other providers where it's already pre-installed. Okay, so now you need to enable the pgVector extension by doing a create extension vector. I've created a recipes database that I'm using for this, for the examples in this talk. So I connected to my recipes database and enabled the extension there. And then I've just done /dx vector to see what it's got to say about the vector and about the extension. I can see that I've got version 0.7.0, which I installed, I upgraded recently, so that's the latest version. And it tells me that it's a vector data type and IVF flat and HNSW access method. So we'll look at what that actually means as we go through. Then if you're using OpenAI, you need to sign up for OpenAI, log in and get an API token, and that's what you're going to use to connect to the API. Now you need some data. Since we're talking about pizza and corn dogs, we're going to load some recipe data. We created a Ruby parser that pulls data from the Armed Forces recipes XML file and loads them into our database. You don't have to use Ruby. As long as there's a Postgres client for the language you want to use, you're good to go. And you don't need to worry about any of the details of this script that we're using, just that it creates a recipes table. It parses the XML file to get the data for each recipe, and then it inserts the name and description for each of the recipes into our recipes table. So you can use any method you want to load data into your database, or you might already have data in your database that you want to play with to try this out. But there is a link at the end of the presentation to all of the code that I've used if you want to try it out yourself with this example. So we've loaded just over 700 recipes. In the real world, as you can imagine, you'll probably be working with much bigger data sets, but that's enough for us just to have a look at how this works. This is our recipes table. So it's a simple table. Each recipe has an ID and a name, and then it has a textual description. So that description includes things like the process, the ingredients, the notes, all the type of things that you would expect to find in a recipe book. And that description is what we're sending to OpenAI for classification. And then we have our embedding column, which is of type vector. That data type vector comes from the pgVector extension. And for interest, this is what the original recipe file for our corn dog looks like. So all of this description is converted to text and put into that description column. Okay, so we've got our data that we want to classify. Now we need to send those recipe descriptions to our OpenAI model for classification and get back the embeddings to store in our database. We've used an OpenAI Ruby gem for that. Again, a link to the code's available at the end. You connect to the OpenAI client using your access token. Submit each of the recipe descriptions to the chosen model. So we're using here the ADA 2 model, and get back the associated embeddings. Then we're writing those embeddings in the database, so they'll go into that embedding field that we created in our recipes table. So that means we've now got the embeddings correlated with the data that we already stored. I've already used the word embedding a lot at this point, but what does that even mean? What is an embedding? So an embedding is a vector, which is an ordered list of, in this case, floating point values. And those values represent the characteristics of something. So that thing could be a block of text, which we're using in our case. It could be an image, it could be a PDF, or all sorts of other things. And we're all used to thinking about 2- or 3-dimensional vectors for things like coordinates. With pgVector, you can create vectors with up to 16,000 dimensions. The OpenAI embeddings that we're using for the model that we've chosen contain 1,536 values that represent the characteristics of the thing we're classifying. So in our case, the textual definition of our recipe. So it looks something like this, only with 1,436 more items. I used the word relatedness back at the beginning of the talk. So the distance between 2 vectors allows us to measure their relatedness, which is how closely related those 2 items are. So the distance between the embeddings that we got back from OpenAI tells us how closely related to our 2 recipe descriptions are. So embeddings for recipes like turkey curry and turkey pot pie might be close together, whereas the embedding for bagels might be further away. It's easy, or certainly for me, it's easy to visualize the distance between points in 2- or 3-dimensional space, and it's fairly easy to calculate that. And although it's not as easy to visualize, the same methods are used to calculate the distance between embeddings. It's just that it's done in many more dimensions. And pgVector is the tool that we're going to use to do those calculations for us. So now that we've got the embeddings, we can start doing queries to show similarities. Okay, we talked about our hypothetical situation where we have somebody in the family that mainly likes pizza, but the rest of the family doesn't want to eat pizza every day. So why don't we use our embeddings to see if we can find some new recipes that are kind of like pizza, but not pizza? Just like the one we saw for the corn dog, this is the original recipe file for our pizza recipe. So we can see what kind of ingredients it uses, and we can see what kind of method we have to use, and we can see some of the nutritional information. If we look in our recipes table and we just select that description where the recipe is called pizza, just so that we can see what we're actually working with in the database, this is what it looks like. This is how it's been converted to text. So it goes on and on. So we can see there's quite a lot of information in there. One of the things that I skipped past, just to let you know, if you do decide to try out some of these recipes at home, just note they are for 100 portions. So if you're doing it for a family, you'll probably want to scale it down a little bit. Okay. So we want to compare the embedding for our pizza recipe against the embeddings for all of the other recipes. So we want to find recipes that have embeddings that are closest to pizza, so the recipes that are the most similar. As you can see on this slide, we can just use a normal SQL query to do this, with the exception of the vector distance operator that I've highlighted in red. So just to be precise, the one that I've highlighted there measures the cosine distance. So this query will display the name and ID of the recipe that we're comparing. So first pizza, and then another recipe that will hopefully be similar. To get the most similar, we're ordering by distance, and then we're using a limit 4 to return just the 4 smallest distances. So just the 4 recipes that are the most similar to pizza. Okay, so what, according to our model, are the top 4 most similar recipes to pizza? More pizza. Okay, pizza, 12-inch frozen pizza. Oh, chicken parmesan isn't pizza. And pizza treats. So maybe our query needs a bit of refining at this point. If 3 of the results are actually pizza of some kind, and only 1 of them is something that's similar to but not actually pizza, we probably want to try again and get things that are at least a little bit different to pizza. So yes, we want it to be like pizza, but we don't want it to actually be pizza. So I just changed the query slightly here. I've just removed the ID and name for pizza because that was the same every time and we don't need to see that every time. And then I've just said that it shouldn't include the word pizza in the name. So let's see if that improves it. Okay, now we're getting somewhere. That's looking a bit more interested. We've still got the chicken parmesan recipe that we had from the previous results, but we've got some new suggestions as well for recipes that are close to pizza but not actually pizza. We've got hamburger with parmesan, eggplant parmesan, and lasagna. And most of those we can probably imagine would be interesting to someone who likes pizza but wants a bit of variety. So let's start digging into some of the details. We used the cosine distance operator in our example, which measures the angle between two vectors, but doesn't take into account their sizes. pgVector also provides an operator to calculate Euclidean distance, so that's the straight line distance between 2 points, and inner or dot product, which measures similarity, which is based on the angle and the size. The taxicab or Manhattan distance operator was added in version 0.7.0. The vector function to calculate that distance had already been added in a previous version, but this operator didn't yet exist. Now, I don't know about you, but I don't have any problem imagining Manhattan distance in 2 or 3 dimensional space, but in 16,000 dimensions, I find it a bit hard to imagine how that works. Which of these operators is better suited for a given application will very much depend on the type of data you have and the type of comparisons that you want to do. There are loads of explanations, examples, white papers, etc. out there discussing the relative merits of each of the operators. So if you're interested, then I invite you to go and read those. Otherwise, it's quite good just to play with the different operators in your query to see what kind of results you get. So those were the vector operators, and each of those has an equivalent function. So you've got the L2 for Euclidean distance, the one for cosine distance, inner product, and then the L1 distance for the taxicab or Manhattan distance. There are other vector functions. These are ones that have been added in the latest version. So you've got binary quantized, normalized with Euclidean norm and subvector. And then you've also got arithmetic operations. So you can do element-wise addition, you can do subtraction, multiplication, and there's also a concatenate operator that was added in the latest version. And then you've got aggregate functions, so you can calculate the average or the sum of vectors. Now, in our case, the average or the sum of a group of recipes seems like a strange concept, but there are scenarios where it does make sense to do that kind of calculation, but I'm not going to try and get into that level of data science. Okay, so I promised that we were going to answer the question, what's the opposite of a corn dog? So it's probably time that we actually had a look at that. So as a reminder, this is what the recipe card for our corn dog looks like. We've got some frankfurters in there, we've got some flour, cornmeal.
You can see me.
Hey.
All right.
Sorry, did you have a question?
Thank you. I joined.
Okay. Okay, so that's the description of our corn dog recipe. To find the opposite, we just need to adapt our original query a bit. So this time, we're going to compare the embedding for the recipe with the name corn dog against all of our other embeddings, and we're going to return the results in descending order. So this time we want the largest distance or the least related first. And this time we're going to use limit 1 to return just the first result. We just want to find the opposite, the recipe that's the least like a corn dog. Okay, so what is the answer to the burning question, the question that everybody's been asking? What is the opposite of a corn dog? Well, according to our recipes and according to the model we've used, it's a green salad, which sounds about right. So what have we actually achieved here? We've created a really simplistic recommendation engine. And although ours is a completely contrived use case, as I said from the start, recommendation engines can be really useful, and it's actually very difficult to avoid them in our everyday lives. So you've got e-commerce recommendations. Just as you're about to check out, you'll be asked, have you also considered buying these similar products? When you finish binge watching your favorite series, you'll get suggestions for other things that you might enjoy watching based on your viewing history. If you've got a health and fitness app, then if you've been logging unhealthy snacks, it might try suggesting healthy alternatives to those, or ways you can increase the amount of activity you do. Social media is constantly suggesting, I don't know, funny cat videos based on videos that you've watched before. Travel apps will suggest hotels or trips that you'll love based on places that you've previously enjoyed. And I'm sure you can think of multiple ways that you could apply this type of thing to your own data. Of course, there are some things that you need to think about when using this kind of tool. For example, storage considerations, performance, resource requirements. Looking at storage, for example, how much space do you actually need to store all of these vectors? Each vector takes 4 times the number of dimensions plus 8 bytes of storage. You can use the vectordims function to find out how many dimensions your vector has. So as I mentioned earlier, the OpenAI model that we're using, the ADA0021, returns embeddings with 1536 dimensions. If you choose to use a different model, then it will return a different number of dimensions. So in our case, that gives us a size of 24 KB per embedding, which, if I've done my maths correctly, is approximately 17 meg for the embeddings for our small data set of 720 recipes, and extrapolates out to about 23 gigabytes per 1 million embeddings. So you can start getting needing a lot of storage quite quickly if you've got large data sets here. I said that pgVector is being very actively developed, and some of the things that have come in the latest version are to allow storing vectors but with less storage. So they've introduced the half vec type, so that takes 2 times dimensions plus 8 bytes of storage for each half vector. And then they've included the different functions and operators to go with that. There's the bit type and then sparse vec type. So it's worth looking at those if storage is a particular concern and if they fit your needs. And I include that partly just to show how much they're doing and how much is being introduced in each of these new version. What about performance? Well, this is Postgres, so you can use all of your usual performance tuning tools. For example, you can use an explain to see the execution plan of your queries. So here you can see that it knows about the distance operator, so it's showing how the opposite of a corn dog query is going to be executed. And you can create indexes to improve performance. By default, pgVector performs exact nearest neighbor search, so that's what we've been doing so far. It provides perfect recall, but isn't necessarily very fast. If you add an index, then pgVector will use an approximate nearest neighbor search, which trades some recall for speed. So unlike typical indexes, you can actually see different results for queries that use an index compared to queries that don't use an index. So that could be a surprise if that's not what you're expecting, because obviously we're not used to adding a query and suddenly getting different results. But in this type of application, usually that doesn't matter. Usually you don't need it to be exact an exact result. Usually an approximation is good enough. So pgVector lets you create two different types of index, IVF flat or HNSW. Comparing the two, IVF flat takes less time to build than HNSW and uses less memory, but it has lower query performance. So that's in terms of the trade-off between speed and recall. It also needs to be trained, so you have to create it once there's data in the table. The HNSW index type, on the other hand, takes more time to build than the IVF flat, and it uses more memory, but it offers better query performance. So again, in terms of the trade-off between speed and recall, and it doesn't need to be trained. So you can create it on an empty table. Whichever of those two types of index you decide to use, you need to create an index for each of the distance functions that you're going to use in your queries. So if you're going to use cosine distance in some queries and you're going to use the taxicab distance in others, you need to create an index for each of those. Okay, so we're going to try a new query just to demonstrate how the indexing might work. This one is using the Euclidean distance, and this time we're going to look for recipes that are similar to chocolate chip cookies. So I've found recipe ID 151 is a chocolate chip cookie. So I've done a limit 5 just to get 5 different recipes that are similar to chocolate chip cookies. Okay, that looks good. I've got 3 different cookie recipes. I've got a toffee crisp bar, 4 different cookie recipes: peanut butter cookies, chocolate chip, chocolate crisp, and chocolate drop. Yum. If we run an explain on that query, we can see that it's doing a sequential scan of our recipes table. I mean, in our case, it's only 720 rows, so you know, that's absolutely fine. It's not taking very long at all. Okay, let's create an HNSW index for the Euclidean distance. So in this case, that's indicated by this vector L2 ops, the Euclidean distance. And then you can specify values for parameters called M and EF construction when you create the index. In simplistic terms, the lower the values of M and EF construction, the faster the index build will be and the smaller the index will be, but at a cost of less accuracy. If you use higher values for those, you'll have a more accurate index, but it will be big and slower to build. So you need to get a balance of those. So somewhere between around 5 and 48 apparently can be reasonable values for M, and double that for EF construction. But again, play around with different values to find out what works for your use case. I've left this error in because it caught me out the first time I tried creating an index. If you try to create an index on the recipes table that we originally created, because we just used the vector data type without specifying a number of dimensions, it complains. It says the column doesn't have dimensions. If you change the data type to specify 1536 dimensions, as we saw, that's the number of dimensions that we have, then it will let us create that index. Going back to the questions of storage and resources, note that HNSW indexes really are big. So the index for 1 million rows of AI embeddings can be 8 GB or bigger. And for performance reasons, ideally you want that index to be in memory. So one of the reasons that HNSW is fast is because it uses a lot of resources. So something to be aware of. There are some query time parameters that you can be aware of. So for example, there is the EF search parameter. It's similar to the EF construction parameter that we saw in the HNSW index creation. This one limits accuracy, but it also limits the maximum number of records returned. So the default value of this is 40, which means that if you try to return 100 nearest neighbors with that default value, your query will actually only return 40 rows. So you just need to make sure if, for example, you want to return 100 nearest neighbors, you need EF search set to at least 100. So smaller value of EF search will give you faster queries, but at the risk of inaccuracy and also a smaller number of values that you can return. So now we've created that index. If we rerun the explain plan to get the execution plan for our choc chip cookies query, you can see that it's now using the index on the embeddings. The eagle-eyed amongst you will notice that it's not actually brought our total cost down by a huge amount, but again, we're working with an extremely small data set, so it's not going to have much impact. And in our case, we still get the same 5 rows returned, but in a larger data set, we'd probably get slightly different results because we're allowing an approximation. And as I said before, in this type of application, that's usually okay. It doesn't matter if we don't get exactly the same results because we want recommendations. We want something that's similar. We're not looking for an exact response. So we saw that pgVector allows vectors to have up to 16,000 dimensions, but note that we can only index vectors with up to 2,000 dimensions. In our case, that's absolutely fine because we're using the model that returns embeddings with 1,536 dimensions, so we can index those. I've read some of the conversations recently on the Postgres mailing lists between Jonathan Katz and others that discuss the reasons for this, which seem to be mainly the Postgres index page size. But it does seem that people are discussing ways where it would be possible to index vectors with more than 2,000 dimensions. So I'd be interested to see how that goes, but I suspect that in future versions we'll see that it will be possible to index index embeddings with more dimensions. At the moment, if you have vectors with more than 2,000 dimensions, there is a technique called dimensionality reduction, which is a kind of compression for vectors. So it turns a vector with a lot of dimensions into a vector that has fewer dimensions, but trying to keep most of the meaningful properties of the original data. With what I've talked about here, we've really only scratched the surface of the type of things that you can do with this and the different options and challenges in terms of storage, performance, etc. If you're working with very large data sets, and you might well be for this type of application, you might need to start looking at things like physically separating your data, caching data, or using various other techniques. And then, as I've mentioned, as we go through, pgVector is in very active development. So even since the first time I gave a version of this talk in February, I've had to make various updates to include information about latest functionality. And I've found the README really, really helpful for finding out how to use the tool, what it does, what's been added in. It's quite clear about what's been added in different versions. So I highly recommend reading that and checking back frequently to find information about the latest versions. And I want to give a lot of credit and kudos to the rest of the team at Crunchy Data because this talk has very much been a team effort and inspired by and leans very heavily on the What's Postgres Got to Do with AI blog post that my colleague Chris Winslett wrote. And he's since written other blogs in the Postgres AI series. So again, wholeheartedly recommend that you have a look at that. I promised that the code would be available so that you can reproduce the things that I showed in the demo today. So there's a link there to the GitHub repo that contains that code. And also I want to shout out to Bob Pacheco, my colleague, who did a lightning talk at last year's OpenShift Commons, where he managed to cover a lot of this material in 8 minutes. So if you don't want to rewatch what I've done and you want to just see a very, very short version of what's pgVector and how does it work, then that lightning talk, I think, is really great. So that's the actual material that I want to present. I really hope that you have fun playing with it. I would always love to hear what people do with it, what some of the less spurious use cases are that you come up with to get value out of your data using pgVector. And I will be really, really happy to chat and answer questions.
Do we have any questions from anyone today? Looks like we do have a comment in chat from Sophia who said that's pretty cool, and it is.
It is, and it's great fun as well. I know, I should be mainly concerned with how useful it is, but it's just fun to play with.
Yeah, sometimes things need to be fun. All right, any other questions or comments? Yes, no? That was very well presented, Karen. Thank you so much. Quinn. Let me find you.
Yeah, I didn't have anything to say. I just thought it was a great presentation.
Oh, great. Thank you. We got a thumbs up from CJ. Pro Ball, Alan, Asai. Excellent. Thank you so much.
But yeah, absolutely go away and play with it and have fun with it.
And Sophia said, thank you so much. Awesome presentation. Great presentation from SI. Perfect. That was a great presentation. Thank you, Karen.
Thanks, everybody.
All right. So in June, SF Pug will not be having an event, but we will be returning on Tuesday, July 9th with Check Your Privileges using the PostgreSQL role system with Christoph Pettis. The next upcoming events are pgconf.dev in Vancouver. And then after that, I'm sorry, that's May 28th through 31st. And then PGEU will be coming up October 22nd through 25th in Athens. We will send you a link by email when the video is ready. And you can also watch our social media, which is expanding. And I will be sending out an email about where you can find us at all the different social media platforms. We do need speakers, as always. So if you're interested, please feel free to get in touch with us, and we would be happy to hear what you'd like to present to us. Thank you so much, everyone. Thank you again, Karen, and I hope everyone has a great rest of your day. Thanks so much.
Thanks, everyone. Thanks, Catherine.
Thank you. Bye-bye.